Okay, we're going to talk about subatomic particles. These are the particles that are inside of the atom. Protons, neutrons, and electrons. Protons and neutrons, where's my pointer? Protons and neutrons have nearly identical masses. These are their actual masses, and we see that they differ only in the fourth significant digit. For all intents and purposes, their masses are identical. And they are very, very small, 10 to the minus 27 kilograms. That's a 0 and a decimal point, and 26 zeros, and then a 1 kilograms. Teeny tiny. The mass of the electron is much smaller, almost 2,000 times smaller. If the proton was the size and had the mass of a baseball, then an electron would have the mass of a rice grain. So that gives you a sense of the relative scale. So a lot of times we'll say that the electron's mass is negligible. It's really close to 0. It doesn't matter. So I live in Reedley, and there's a lot of fruit that grows around there, and some nuts. I live in the land of the fruit and the nuts. Question is, which one am I? I'm a nut. So big semi-trucks full of fruit. This time of year, it's peaches and plums and things. And so they have to go to the public scales and weigh before they can go off and do whatever it is that they do with that. So imagine a semi-truck with its trailer just full of peaches, and it goes and it weighs at the scales. And then as they're pulling off, a guy comes up behind, hey, you forgot one, and he tosses one peach up on top of this big load. Is he going to have to go back and weigh because of that one extra peach? Is that going to matter? No. The peach has mass, but it is so small relative to the mass of the truck that it doesn't matter at all. So that's why we often consider the electrons to basically have no mass, because they're like that one extra peach thrown on the big truck. It just really doesn't matter. So as we see in this picture, in this slide, kilogram is not a great unit for measuring the mass of these particles because it gives us these incredibly small numbers. And even the smallest metric prefix is still not going to be small enough. So there is a unit that was made just for measuring the mass of atoms and their subatomic particles. It's called an atomic mass unit. How's that for just, really clever and inspired, right? At least it's descriptive. So an atomic mass unit is a unit for measuring the mass of an atom. The abbreviation is AMU. It's kind of got a funny definition. 1 AMU is 1/12 the mass of a carbon atom containing 6 protons and 6 neutrons. Okay? A carbon atom with 6 protons and 6 neutrons has a mass number of 12, right? And so basically we're saying that 1 atomic mass unit is the mass of a proton or a neutron, roughly speaking. Right? So proton or neutron is approximately 1 AMU. Some of these particles have charges, right? The proton has a positive charge, the electron has a negative charge. Those charges are equal in magnitude. Here we have the actual charges in coulombs. We're not going to use these numbers much, if at all. But notice that the numbers are the same. The positive is for the proton, P, proton positive. The electron's negative. So instead of using these messy numbers and measuring it in coulombs, what we usually do is we just talk about relative charge. The proton is +1, the electron is -1. The neutron is neutral, it has no charge. Here are the actual masses in kilograms. We don't use those very much. You might have to refer to that for an occasional homework problem. Don't even try to memorize those. It's the atomic mass units that we need to remember. And we don't even need this much detail. We're going to say this is approximately equal to 1, approximately equal to 1, and we're going to call this approximately 0. It's that peach thrown up on top of the big truck. Doesn't matter. So these are the numbers that you need to know. Proton has a mass of 1 atomic mass unit and a charge of +1, etc. Okay? Yeah, that's that slide. So matter is usually charge neutral, meaning equal numbers of positive and negative charges. Protons and electrons in equal numbers. Charge imbalances can occur, but they usually equalize quickly and often very dramatically. An example is lightning. Lightning is an equalization in the imbalance caused by storms. And so you get a negative charge building up in the clouds, a positive charge building up on the ground. The lightning strikes and it equalizes the charge. Another example is static electric shocks. You know, so you rub a balloon on your head and it makes your hair stand up, and if you touch it, you can give a little spark, right? That's charge imbalance equalizing. So elements are defined by their numbers of protons. This is called the atomic number. It's given the symbol Z, which in English makes like 0 sense, right? Z for 0, 0 cents. It's from the German Zahl, which means number. So it'd be like, you know, N or something. So the atomic number has the symbol Z. That is equal to the number of protons. So in a helium nucleus, here's a helium balloon. In the helium nucleus, there are 2 protons. That's what identifies an atom as being helium, if it's got 2 protons. In a carbon nucleus, like in the graphite in your pencil, there are 6 protons. Every carbon atom has 6 protons. If you have an atom with a different number of protons, it's not carbon. On the periodic table, we have the atomic numbers for all of the elements. So we can look at beryllium here. Here's the chemical symbol. This periodic table has the name as well. And above the symbol is the atomic number, the number of protons. So we don't need to memorize how many protons different elements have. We just look it up. If we're interested in copper, we find copper here, and how many protons does the copper atom have? 29. Okay, it's all in the periodic table. So you have memorized a lot of the chemical symbols. You guys as a section did really well on that memorization quiz. The other section didn't do as well. And I choose to believe that you guys just have been studying more, although part of me suspects that maybe they shared which things were on the quiz with you, but I have no evidence of that, so we'll choose to believe the best. No, you guys are you're just doing good. So the chemical symbol. Chemical symbol is either 1 or 2 letters. The first letter is always capitalized. If there's a second letter, it is never capitalized. And we need to be careful in how we write these. We have to be precise, okay? And I know some people don't like that, but there are places where we have to be. So for example, the element tin has the abbreviation capital S, lowercase n. I know that some people like to write in all caps, and so they want to write this like this. And they say, well, that's my lowercase n. Not for chemical symbols, it isn't. You need to make an actual lowercase n when you write the element symbols. The rest of your writing, I don't care, as long as somebody can read it, okay? This is not okay. We also need to be really careful about size, because some letters, the only difference between uppercase and lowercase is their size, right? And so the element cobalt is capital C, lowercase o. But if our O gets too big because we're being sloppy, it's carbon monoxide. Carbon monoxide and cobalt are very different things, okay? When we type, like doing mastering chemistry homework, most things are easier to distinguish. There's one thing that causes problems, though. What's that? Iodine or 1, or it could be a lowercase l, right? They look the same when you type them into Mastering Chemistry. I recently changed the font that I use on my on my slides because the font that I used previously, a 1, a capital I, and a lowercase l all look the same. Bless you. I write my 1s like that, just a line. For a capital I put bars on the top and the bottom. And for a lowercase l, I make it a script L. Not necessarily in all words, but when I'm writing element symbols. Because aluminum is a lowercase l. When I write it like this, AL, sometimes students misunderstand and they think that's A capital I, or sometimes they say A capital L. It gets all mixed up. There is no element A. But I just want to caution you, be careful with that. So many of the chemical symbols, most of them in fact, are based on the English element name. So helium, that makes sense. It's the first 2 letters of the name. Carbon is the first letter of carbon's name. But some of them are based on Greek and Latin names. And these are usually the elements that have been known about much longer. So sodium has the symbol Na. Where the heck did they get that? Sodium doesn't have an N or an A in its name. That's because the symbol came from the Latin name natrium. And sodium was named for the sea because that's where they found it from. There's sodium ions in the ocean, natrium. So those ones that seem like just totally disconnected, it's from the Latin names. So all atoms of a given element have the same number of protons. They don't necessarily have the same number of neutrons. So if you have atoms, get the same number of protons, but the number of neutrons is different. Those are called isotopes. So the prefix iso means the same. So they're the same element, but they're slightly different types of the same element. Okay, they're called isotopes. For the element neon, all neon atoms have 10 protons. Every single one of them. But some of them have 10 neutrons, some have 11, some have 12 neutrons. Protons and neutrons are the particles with mass, significant mass inside the atom. So if you're having different numbers of neutrons, that's going to slightly change the mass of the atom. Right? So we've got 3 different isotopes for neon, and each of them has a slightly different mass. And so this is, when this was discovered, we realized we had to modify Dalton's atomic theory a little bit because he said that all atoms of a given element are identical, had the same mass. Now we know, not quite. They all have the same number of protons. Well, so neon has 3 isotopes. Does that mean that if you had a sample of neon, it would be 1/3 of each? No. Each element has its own distribution between however many isotopes it has. And this information is not available from the periodic table. Some elements only have 1 kind. Some have 3, some have 2. It just varies. Why? Just because it is. That's just how it is. So we can look at an element and study the different atoms in it, and we find that no matter where we get the sample from, the distribution is very close to the same. We call this the natural abundance. Natural abundance of isotopes. Yes?
Do we see this in man-made chemicals or elements?
That's a good question. Do we see this in the man-made elements? So the man-made elements, the reason that we never find them in nature is because they are so unstable. They're actually radioactive and they fall apart. And so when you look at the man-made elements on the periodic table, you'll see that their atomic mass, which we'll talk about in a minute, underneath is just a whole number in parentheses. And that's because these are so unstable that we can't even get an accurate mass for them. So if they have isotopes, we have no way of knowing. But that's a good question. So we need a way to specify which isotope we're talking about. Sometimes we care which isotope we're talking about. Most of the time we don't, but sometimes we do, so we need to specify it. So we talked about the atomic number. That's the number of protons. We have another number called the mass number, and that's given the symbol A. It's the number of protons plus the number of neutrons. And so we can write symbols in this form where we use the chemical symbol, that's where the big X is, and as a superscript on the left, we write the mass number, and as subscript on the left, we write the atomic number. And so the three isotopes of neon would be shown here. So here's neon. They all, notice the subscript there is all the same. They all have 10 protons. And the number on the top is giving us the sum of protons plus neutrons. So this actually works out fairly conveniently. So let's do this one. Okay, so that's the symbol for that middle isotope. If we want to know how many neutrons this one has, we just subtract. 21 minus 10, this one has 11 neutrons. That's how I remember which number to put on the top and which one to put on the bottom. They're stacked up so that you could subtract them and get the number of neutrons. Is that why they did it? Probably not, but I like to think so. I make up reasons for things and it helps me remember. Okay? Any questions? So that's one way to specify an isotope. Another way, because that can be tedious, especially typing it into a computer, the stacked subscripts, superscripts, really a pain in the neck. We can also do it this way, use the chemical name or the chemical symbol and a dash followed by the mass number. Because do we really need the atomic number in the symbol? No, because we have the periodic table. So, you know, neon 20, bless you. This is the mass number. If we need to know the number of protons, we just look it up in the periodic table. Periodic table should always be available. I have an app on my phone, right, because I'm a chemist and I can't be without a periodic table, and I even carry one around on my cup. It's got everything on there. I can't read most of the words, but it still makes me feel good just to have my periodic table. So we can symbolize this as Ne20 or neon 20, neon 21, neon 22. Question?
When it comes to the exam or quiz, do you prefer one over the other?
That's a good question. So, you know, which one of these would I prefer on a quiz or an exam? So these sorts of questions will show up as multiple choice questions on an exam. And I don't intentionally try to trick you unless I warn you about it ahead of time. And then is it really tricking you? I don't know. If I asked you for the symbol for, say, the neon atom with 11 neutrons, I would not give you both of these and expect you to say that one was better than the other. There would be one that's correct, and the others would be incorrect in some way. Okay? We do need to be able to recognize and understand what all three types of symbols mean. Any other questions? So here's a table with some information about those three neon isotopes. So we can write their symbols over here. Here we see that the number of protons is the same for all of them because they are all the same element. The number of neutrons is different, and the mass number is the sum of the protons plus the neutrons. So when we specify the mass number, that tells us which isotope it is. This is the natural abundance in percentage form. 90.48% of neon is neon 20. Teeny tiny bit is neon 21, and just less than 10% is neon 22. Why? Because it just is. You can go out and study neon and find it, and it's always these percentages. That's just how it naturally is. Any questions? There's nothing in this table that you need to memorize. Okay, yeah.
So the natural abundance depends on the number of isotopes for the different isotopes for a certain element?
Yeah, the natural abundance will be different for each element. If there's only one isotope, obviously it's 100% that one. But it's not like 50-50 or 33-33-33. It will be different for each element, and that's not information we get from the periodic table or anything. If we need it, it would be given to us. Okay? Or we would be given the information so that we could calculate it, and we'll talk about that in just a minute as well. So just say something else, but it's gone. So we should be able to answer questions like this. What are the atomic number, the mass number, and the symbol for the carbon isotope with 7 neutrons? Well, let's find carbon here on the periodic table, right? Here's carbon. What does the periodic table tell us about carbon? It has 6 protons, right? So what is its atomic number then? Atomic number. The atomic number is 6, okay? And that's the symbol Z. Atomic number is 6. I always think that the atomic number should be A, right? Wouldn't that make more sense? It's backwards, so that's, I remember, no, it's the other. The atomic number is 6 because element 6 is carbon. That means it has 6 protons. Then it asks us for the mass number. So the mass number, A, is protons plus neutrons. Well, we just figured out how many protons it has. It has 6. How do we know the number of neutrons? Well, they told us. It's 7. So 6 plus 7, 13. So that's the mass number. I can't get that from the periodic table. And then the symbol. So if this was a question where you're just handwriting the answer, I would accept any one of the 3 symbols. But we're going to do them all. So we could call this carbon 13. We could call it C13. Or we could draw the nuclear symbol where we put the mass number on the top and the atomic number on the bottom to the left of the symbol. Any questions about that one? I believe there's a question in Mastering Chemistry, or it gives you a table, and it'll give you some pieces of information and ask you to figure out the other ones. Question?
How do we know if there are 7 neutrons?
Because it says right here.
Oh, yeah.
Yeah, 7 neutrons. But sometimes it'll maybe give you, like if they said, oh, C13, how many neutrons does it have? Well, you have to figure out from the periodic table how many protons, and subtract that from 13 and say 7 neutrons. The nice thing about this is the math is really simple. It's adding and subtracting whole numbers, right? Then we can answer questions like this as well. How many protons and neutrons are present in an atom of this? Now, if I had to read that, how do you read that? I'd probably call that K39 or potassium 39, because I don't know how else to read that. How many protons does it have? Protons. 19. So it's got 19 protons. That's this right here. Okay, we could also get that from the element symbol looking at the periodic table, 19. To get the number of neutrons, we're going to subtract. Right? So let's undo that. We're just going to subtract here. 39 minus 19 is 20. On an exam, go ahead and do that subtraction with your calculator. You don't want to have a brain fart make you mess up and get an answer wrong. So 20 neutrons. Any questions? So the number of protons in the nucleus is like the soul or the personality of an atom. It doesn't change. It's always the same. And so we think about people. I like to personify atoms and things because they are so abstract that it helps if we bring them into something we understand and make them into people. You think about people. You can change your appearance, right? You could have cosmetic surgery. You can shave your hair off. You can do all kinds of different things or just dress yourself differently. If you want to shut that door, that's fine. Makes you look different. Does it change who you are? No. You are still you. Whether you like it or not, you are you. The number of protons that an atom has never changes. Okay? The number of electrons can change. So protons and neutrons are at the core in the nucleus, and the electrons on the outside. So I think of the electrons as being a little bit like the clothing that the atom is wearing. You can take a hat off, you could put a sweater on. Atoms can add electrons and they can lose electrons. When that happens, because the number of protons doesn't change, they get a charge, okay? It could be a negative charge or a positive charge. But a charged particle is called an ion, okay? If it's positively charged, such as Na+, that's a cation. And negatively charged ions, like F-, are called anions. So we need to know that cations are positive and anions are negative. The way I remember this is I happen to like cats. I have positive feelings for cats. Even the cat that threw up on my toothbrush. Right? What is it? But I still like them. I don't know. I don't know why, but I do. Cations are positive. Anions are negative. Okay, so if you don't like cats, that's not going to work for you. You got to come up with something else. If you look at these words, they both end in ion, but this one starts with an. It's got an extra n in it, and that's the negative one, if that helps you at all. Okay, so gaining or losing electrons is how we get the ions. Any questions?